Hi everyone, my name is Avin, and today I will be talking to you guys about the topic of chemical equilibrium. First off, what is equilibrium? Well, for starters, the whole concept prospered when a French chemist by the name of Claude Louis Berthollet discovered that certain chemical reactions are reversible, meaning that the reaction could also proceed to go backwards and products could react to form reagents. He then stated that for any reaction to exist at equilibrium, the rates of the forward and reverse reactions must be equal. A dynamic equilibrium is a state that can only occur within a reversible reaction. The substances in the system transition back and forth between reactants and products at equal rates, and because of this, the concentration of both of these experience no net change. What influences this? Well, there are two main factors that influence equilibrium: concentration and temperature. The concentration vouches for how often collisions take place. Fewer collisions take place in between the molecules when they are in a state of low concentration. This in turn would mean that the reaction would happen at a slower rate. The opposite is also true. If the concentration of the reactants is high, the reaction will occur at a faster rate. Temperature, which can be used to explain the energetics of collisions. Lower temperatures mean lower energy collisions and therefore lower energy reactions. Vice versa is true for higher temperatures. There are so many different things you can do to a system that will cause absolutely zero shift in equilibrium, such as the addition of a catalyst or an inert gas. You can see in the graph here on the bottom that the only thing the addition of a catalyst does is speed up the rate of the reaction. It does not affect the positioning of equilibrium. However, this is where we can start to talk about Le Chatelier's principle. It states as follows: changes to an equilibrium system will result in a predictable shift that will counteract that change. He covers the concentration, pressure, and temperature effects. Le Chatelier deemed reversible reactions to be quote-unquote self-correcting. So when the reaction is thrown out of balance by one of these three factors, a natural shift will occur to compensate for it. Let's talk about concentration first. When you increase the concentration of the reactants, it will impose a stress on the system. To counteract for this, the system will create more products and equilibrium will shift to the right, and the system will be at equilibrium once again. You can see this happening in the image above. The system shifts to the right in order to create more products and restore equilibrium. If you think about it, reducing the concentration of products will also result in the same shift. Although, if you look on the bottom, adding or increasing the concentration of products will cause the system to shift to the left in order to be able to produce more reagents. And again, if we were able to remove reagents, the same outcome will occur. Next, we have pressure. A change in pressure or volume will cause the equilibrium to restore itself by either creating more or less moles of gas, depending on the stress that is imposed on the system. Volume and pressure are inversely proportional. So, when you reduce volume, you are also increasing pressure, which will cause the equilibrium to shift to the side with fewer moles of gas present, because a smaller volume means that there's less available space, as you can see on the bottom image on the screen. On the other hand, when you increase volume and decrease pressure, the equilibrium will shift to the side that produces more moles of gas since there's more space available. Last, but certainly not least, we have temperature. The concept of temperature changes in equilibrium is directly related to the heat of the reaction. The reaction is either absorbing heat, which we know as endothermic, or it is releasing heat, which we know as exothermic. An increase in temperature shifts the reaction towards the endothermic direction, and a decrease in temperature shifts it in the exothermic direction. It is also important to note that temperature has a direct effect on the equilibrium constant. In an exothermic reaction, K, the equilibrium constant, decreases as temperature increases, and in an endothermic reaction, both values increase. The equilibrium constant, as I previously mentioned, is referred to as the letter K. It can be used to describe the relationship between starting reactants or products at equilibrium, depending on the direction of the reaction with respect to a specific characteristic such as concentration or partial pressure. As you can see on the screen, a reversible reaction, the products are divided by reactants and each concentration is raised to the power of its molar value. products are divided by reactants, and due to the concentration values being measured at equilibrium, the equilibrium constant will not change. We can then use the value of K to determine whether the equilibrium favors products or reactants. If K is greater than 1, products are favored, and if K is less than 1, reactants are favored. We can now talk about the reaction quotient. The reaction quotient can be referred to as K, and its value provides us with the amount of products and reactants present at a distinct point. It is calculated in the same way as K, but instead evaluates concentration values at a distinct point in time when they are not in equilibrium. We can compare the values of K and Q to determine the direction that the reaction is shifted towards. If K is less than Q, the system will be shifted to the left, and reactants will be favored. If K is greater than Q, the system will be shifted to the right and products will be favored. If K and Q are equal, the system is at equilibrium and no shift will occur, nor will any side be favored. We can further expand from what we just talked about and use it to predict the direction of a reaction. For this, we will need to compare the value of K with the value of Qi, the initial reaction quotient. Once we obtain our K value, we can use the same formula for Qi and plug in the initial concentrations of products and reactants. If Qi is greater than K, the reaction will occur in the reverse direction. If Qi is less than K, the reaction will proceed in the forward direction. K can also predict the reaction's tendency to go to completion. If K is large, the reaction will tend to proceed to completion and the system will contain mostly products. If K is small, the reaction will most likely not occur and mostly reactants will be present. Take a look at this example problem and think about it before proceeding to the next slide and see if you can figure it out before I move on to the solution. So starting off with our original reaction, we are first going to write down all of our given values. So we have a K of 2, an initial concentration of 8 molar for H2O, and an initial concentration of 6 molar for CO. Next, we are going to construct our ice table, and I personally think it's best to write down the balanced equation over top just so it gives us a nice basis for what we are doing. And we're just going to write down our variables, and we have 8 for H2O, 6 for CO, 0 and 0 for our products, and then minus x and plus x, 8 minus x, 6 minus x, x and x. And it's also good to note here that H2O is not negligible because it's a gas and not a pure liquid. And then we are going to write our K expression, so products over reaction raised to their molar power, which in this case we're lucky and it's just 1. And once we have plugged in our actual values, it's pretty clear that we are going to need the quadratic formula, so we can start solving for that and get it into a nice quadratic form before we are able to plug it into the actual formula. So once we've gotten up to this far, we can actually FOIL out these numbers to get 96 minus 16x minus 12x plus 2x squared minus x squared equals 0. And then x squared minus 28x plus 96. Now we have it in nice quadratic form. Then we can plug into the quadratic formula. So negative b plus or minus the square root of negative b squared minus 4ac all over 2a. And we have 28 plus or minus negative 28 squared minus 4 times 1 times 96 over 2 times 1 is just 2. Once we've gotten that far, we can multiply all the variables to get the square root of 400 over 2, and we end up with two values, x equals 4 and x equals 24. And over here, 8 or 6 minus 24 will both be negative numbers, so it's pretty clear that our value that we need to use here is 4. Plugging it in back into our K equation, we can get all the values at equilibrium. So for H2O at equilibrium, we have a value of 4. For CO, we will have a value of 2. And for CO2 and H2, we will have values of 4. Now, we were originally given a K of 2, and we can confirm this and plug back in our values at equilibrium and to see what we end up with. And as you can see here, we end up with the same K. So it's clear here that even though the concentrations do change, the K value stays constant. Can you think of a place where we see equilibrium in our everyday lives? Equilibrium is everywhere. Think about the last fizzy drink you consumed. Maybe it was a soda. Have you ever noticed that when you leave the cap of your soda off for too long, all of the carbonation seems to go away and the soda is then said to be flat? The concept of equilibrium actually explains this very well. Carbon dioxide is the agent that provides carbonation in all of our fizzy drinks. In a soda bottle, it is present inside the bottle and has been dissolved into the liquid. But there's also carbon dioxide gas present in that little empty space between the liquid and cap. The carbon dioxide is constantly moving, undergoing both evaporation and condensation. Before you open the soda cap, the equilibrium is occurring within a closed system, and as we all know, that is a very important factor. So as soon as you open it, that is no longer the case. The carbon dioxide gas can escape, and you can actually see this on the slide here if you look closely at the photos. And because this happens, it causes a stress on the equilibrium. So in turn, the dissolved carbon dioxide starts to undissolve back into a gas to compensate for the lost carbon dioxide gas. And that's why your soda can go flat, because if left open for too long, all of that carbon dioxide gas escapes into the surrounding air. Thank you so much for listening. My references can be found on the next 2 slides.